Let's take up general characteristics of compounds of alkaline earth metals. The dye-positive oxidation state of alkaline earth metals is shown by group 2 elements. The oxides and other compounds of beryllium and magnesium are more covalent than formed by heavier and large size member. Reason being that their ionization enthalpy is high, and due to smaller cation they have high polarizing power and more tendency to form covalent compounds. Oxides and hydroxide alkaline earth metals burn in oxygen forming monoxide, except beryllium have rock-like structure, rock salt-like structure, that is NaCl type structure, which has face center cubic with the coordination number 6. Beryllium oxide is essentially covalent in nature. The enthalpy of formation of these oxides are quite high, and consequently they are stable to heat and have high melting and boiling point due to high lattice energy. Beryllium oxide is amphoteric like aluminium oxide, while oxides of other elements are ionic in nature. All these oxides except beryllium oxide are basic in nature and react with water to form sparingly soluble hydroxides, and solubility of hydroxides increases down the group because hydration energy dominates over lattice energy. Solubility and thermal stability and the basic character of these hydroxides increase with the increase in atomic number from magnesium hydroxide to barium hydroxide. Beryllium hydroxide is amphoteric in nature and reacts with both acid as well as alkali. After that, magnesium hydroxide is a weak base, barium hydroxide is a strong base. Magnesium hydroxide is sparingly soluble in water, whereas it forms suspension, whereas barium hydroxide is readily soluble in water because its hydration energy dominates over lattice energy. Beryllium hydroxide reacts with OH ion to form berylliate ion, and beryllium hydroxide reacts with HCl to form this complex. Shows that it is soluble in both NaOH as well as HCl, so that is, it is amphoteric in nature. Halides. Except beryllium halides, all other halides of alkaline earth metals are ionic in nature. Beryllium halides are essentially covalent because of high polarizing power of beryllium ion, which is due to smaller cation. Because these are covalent, that's why they are soluble in organic solvents. Beryllium chloride has a chain structure in the solid state as shown below because it is Lewis acid or electron deficient. Therefore, it forms polymeric chain structure in solid state. In gaseous state, it forms a dimer. The beryllium chloride is linear molecule, and it also forms dimer in vapor state by forming coordinate bond, because chlorine has lone pair of electrons, so it can form coordinate bond. So there are chlorine bridges in the dimer of BeCl2, but this only is formed in gaseous state. In vapor phase, beryllium chloride tends to form a chloro-blitzed dimer which dissociates into linear monomer at high temperature at the order of 1200 Kelvin. The tendency to form halide hydrates gradually decreases because size increases. MgCl2 into 8H2O, CaCl2 into 6H2O, SrCl2 into 6H2O, and barium chloride into 2H2O. That is, number of water molecules which are associated with them goes on decreasing due to increase in ionic size and therefore decrease in hydration energy. The corresponding hydrated halides of beryllium and magnesium on heating suffer hydrolysis. The fluorides are relatively less soluble than the chlorides due to their high lattice energy. And why they get hydrolyzed? The halides of beryllium and magnesium, because they are covalent. So on hydrolysis they form hydroxide and HCl, due to which they fumes in moist air. The metals combine directly with halogens on heating at appropriate temperature, forming the halides of the general formula Mx2. The halides can also be obtained by reacting metal carbonates with dilute halogen acids. Beryllium halides BeF2, BeCl2 on account of smaller size of beryllium ion are covalent, therefore do not conduct electricity in molten state. They are hygroscopic, that absorbs warm moisture from atmosphere and also fume in moist air due to hydrolysis. They sublime on heating. Anhydrous beryllium halide cannot be obtained from the material made in aqueous solution because of the hydrated ion like BeOH 4 times Cl2 or BeOH 4 times F2 are formed. Attempts to dehydrate them result in hydrolysis. So the way is, when you heat them, we get hydroxide and HCl. For fluoride, we can use indirect method. Beryllium oxide reacts with ammonia and HF to form ammonium berylliate, fluoroberylliate, which on heating gives BeF2 and ammonium fluoride. Similar is the case with MgCl2 into 6H2O. If we pass dry HCl gas, we can get anhydrous. On heating, we cannot get anhydrous MgCl2. Salts of oxoacid. The alkaline earth metals also form salts of oxoacid. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of ammonium or sodium carbonate solution to the solution of soluble salt of these metals. Solubility of carbonates in water decreases down the group because lattice energy dominates over hydration energy. All these carbonates decompose on heating, giving carbon dioxide and oxide, but the temperature at which they decompose goes on increasing down the group due to increase in lattice energy and ionic character. Beryllium carbonate is covalent, it's unstable and kept only in atmosphere of carbon dioxide. The thermal stability increases with the increase in cationic size. Next we are taking sulfates. Sulfates of alkaline earth metals are white solids and stable to heat. Barium sulfate and magnesium sulfate are readily soluble in water because they have high hydration energy. The solubility decreases from calcium sulfate to barium sulfate because lattice energy dominates over hydration energy. The greater hydration enthalpy of beryllium ion and magnesium ions overcome the lattice enthalpy factor, therefore their sulfates are soluble in water. Solubility of sulfates follow the order. BeSO4 is more than MgSO4 is more than CaSO4 and is more than strontium sulfate, and then barium sulfate and radium sulfate is least soluble. Significantly high solubility of BeSO4 and MgSO4 is due to high enthalpy of solvation of smaller beryllium and magnesium ion. Asbestos is a fine-grained form of gypsum, CaSO4 into 2H2O, which is shiny like marble and is used to make ornaments. CaSO4 is slightly soluble in water, therefore objects made from asbestos or gypsum cannot be kept outdoors. Epsom salt MgSO4 into 7H2O is used as mild laxative or purgative, which is used in medicines when you have constipation. Barium sulfate is used as white pigment. Calcium sulfate can exist as hemihydrate, which is called plaster of Paris, and it is used as building material. This is made by partial dehydration of gypsum at 373 or 393 Kelvin. Barium sulfate is both insoluble in water and opaque to X-ray and is used in barium metal X-ray to provide a shadow of the stomach or duodenum on X-ray picture, which is useful in diagnosing stomach or duodenal ulcers. Sulfate of all decompose on heating. MgSO4 on heating gives MgO plus sulfur trioxide. The order of stability, beryllium sulfate is less stable than MgSO4, is less stable than CaSO4, than SrSO4 and BaSO4. That is due to increase in lattice energy. Nitrates. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes at anhydrous salt. All of them decompose on heating, giving metal oxides, nitrogen dioxide, and oxygen. So metal nitrate on heating gives metal oxide, nitrogen dioxide, and oxygen. And the metals, beryllium, magnesium, calcium, strontium, barium, all decompose in the same manner. All nitrates are soluble in water because in nitrates, hydration energy dominates over lattice energy. Why does solubility of alkaline earth metals, hydroxide, increases in water down the group? Reason is alkaline earth metal hydroxides, the anion being common, the cationic radius will influence the lattice enthalpy, and as the size of the cation increases, the solubility increases because hydration energy dominates over lattice energy. So lattice energy decreases and hydration energy dominates, that's why the solubility increases. Anomalous behavior of beryllium. Beryllium has exceptionally small atomic and ionic size and does not compare well with the other members of the family. It has high ionization enthalpy and high polarizing power, therefore its compounds are largely covalent and easily hydrolyzed. It does not exhibit coordination number more than 4 as its valence electrons. There are only 4 orbitals and it does not have d orbital, therefore it cannot show covalency of 6 by using d orbitals, which others can. The oxides and hydroxides of beryllium are amphoteric, whereas others form basic oxides and hydroxides. Next we take diagonal relationship between beryllium and aluminium. The ionic radius of beryllium ion is estimated to be 31 picometer, and the charge over radius ratio is nearly same as that of aluminium ion. Like aluminium, beryllium is not readily attacked by acid because of the presence of an oxide film on the surface of metal. Beryllium hydroxide dissolves in excess of alkali, forming berylliate ion in the same manner as aluminium hydroxide dissolves to form aluminate ion, or meta-aluminate ion more accurately. The chlorides of both beryllium and aluminium form chloride ion bridged chloride structure in vapor phase with the formation of coordinate bond. Both the chlorides are soluble in organic solvents and or strong Lewis acid, and they are used in Friedel Craft reactions so as to generate electrophile. Beryllium and aluminium ions both have strong tendency to form complexes BeF4 2- and AlF6 3-. Only difference is that highest covalency of beryllium is 4 and aluminium is 6, because beryllium does not have d orbital, aluminium has d orbital.